Okay, now want to modify our analysis using the fact that for no nuts we got an omega of 3.4 radians per second squared, meaning we had some restoring force constant here that gave rise to this angular frequency. Now, we don't know the moment of inertia, and we don't know what the restoring force constant was on that first system, on the unloaded system. By unloaded, I mean we've got all the nuts and bolts in the wheel that were originally there, but we're not adding any nuts or any washers. Okay, so that's what I mean by unloaded. Now, from this, we want to infer, from all this data, we want to infer the effect of the unbalanced wheel and get a better estimate of our moment of inertia. So if we let kappa naught, I'm going to use kappa now instead of K, since I'm doing this just on video and you don't have to worry about a blurry board. Although I had an erasure, I started with K, and so that kappa might be a little bit difficult to see. Not a big deal. Okay, we're going to let kappa naught be the restoring torque constant for the unloaded wheel. Now, we don't know what the restoring torque constant is. We don't know what the moment of inertia for the unloaded wheel is, but we do know omega for the unloaded wheel. So we have a relationship among the moment of inertia and the restoring torque constant, kappa naught, I'll call it kappa naught, and the angular frequency omega naught, where omega naught is the 3.4 radian per second squared frequency, angular frequency that we observed. Okay, so we've got that. Now, what can we say about the situation with 4 nuts? You might want to think about that. You might want to pause and think just a little bit and see if you can come up with some ideas. If you pause, great. If not, well, I'm going to continue and hopefully give you some ideas. Okay, now if there are 4 nuts, then we'll call this kappa sub 4, going to stand for the restoring torque constant here. Well, that's just going to be kappa naught plus the restoring torque constant that we would get as a result of 4 nuts. And that restoring torque constant, let's see, got to go back and remember what we got before. I think it was something like 0.0044. If I'm fading out, it's because I'm walking over here because I didn't have that handy. Yeah, okay, that's going to be 0.1 meter times the mass of now 4 nuts, each nut being 4.5 grams. That's going to be 0.018 kilograms. And that's going to be times the acceleration of gravity, g. So that's going to be kappa naught plus 0.0018, but then times g is going to give us, so it's going to be 0.018 kilogram meters squared per second squared. And let me pause and make sure that I'm right with all my units and so forth, and you want to check me on that too. Okay, that works. If you multiply that, that's actually a meter Newton, which is a unit of torque. And if you divide that by an angle, the sine of an angle, or by an angle theta in radians, you're still going to get units of torque. So that's a correct unit. Okay, now I've also called this I removed the zero because you have just one moment of inertia. Actually, the addition of 4 nuts does increase the moment of inertia, but by a small amount that we're going to ignore for right now. We could take that into account, and it wouldn't be any big problem, but let's keep it as simple as we can. Okay, so we got the moment of inertia, the restoring torque constant for the situation where we have 4 nuts, and of course now we know that the moment of inertia is going to equal restoring torque constant divided by the square of the angular I want to say angular velocity, but the angular frequency, 4.9 radians per second squared. So we know this. We have an expression for kappa 4 and another expression for I. The expression we have for kappa 4, the only unknown is kappa naught. So when I complete this expression, I'm going to have just an equation in the unknowns I and kappa naught. Everything else is known. This is known, this is known. And we're going to be able to combine that with this equation and solve for both I and kappa naught. So if I write this out, I get kappa naught plus 0.018 kilogram meters squared per second squared. Probably can't read that unit, but there it is. And omega 4 squared. Omega 4 is 4.9 radians per second, so we're going to get about 24 radians squared over second squared. Now the second squared here will divide the second squared, the reciprocal second squared in the numerator, reciprocal second squared in the denominator, divide out, and we end up with just kilogram meters squared over radians squared. The meter squared divided by the radians squared means that we're taking a meter of arc and changing it to meter of radius, and we're still going to get kilogram meters squared up here. So that's going to equal kappa naught over 24. Actually, I'm just going to keep it like that, because when we set up the equation, you'll see what happens. Okay, well, this is I and this is I, assuming again that the moment of inertia hasn't changed too appreciably. So what we get is this expression is going to be equal to this expression. So we're going to get kappa naught over omega naught squared. Now omega naught's 3.4 radians per second squared. This is going to give us something on the order of about 10.4 radians squared per second squared. And that's going to equal our kappa naught plus 0.018 kilogram meters squared per second squared divided by 24 radians squared per second squared. Now that's an equation that we can solve for kappa naught. But we can take care of the denominators. Let's just multiply this by 24, multiply this by 10.4. The radians squared per second squared can be divided out of the equation, and we're going to get, well, let's put it this way, 24 kappa naught equals 10.4 times kappa naught plus 0.018, and I'm at it again, it's kilogram meters squared over second squared. I can't even read that, but we understand that's kilogram meters squared per second squared. So when we multiply through by the 10.4, subtract the 10.4 kappa naught from this, we're going to get sorry, I'm just looking at something. We're going to get 13.6 kappa naught equals 10.4 times 0.018. That's going to be something on the order of 0.18, but then less 4%, which would be less like 0.07. I'm just going to say that's about 0.17 kilogram meter squared per second squared. And I've been carrying this error all the way through. That's too big. 0.1 times 0.018 gives me an extra 0 here. So let's correct that as best we can. It's going to be a 0.017. Okay. And now when we subtract, when we divide 0.017 by 13.6, we're going to get kappa naught equals about 0.0012 kilogram meter squared per second squared. Having obtained kappa naught, I can plug that into this equation where omega naught is 3.4 radians per second squared, so that we find that I, the moment of inertia, is kappa naught over omega naught squared equals what? 0.0012 kilogram meter squared per second squared, finally writing that to where it's at least halfway legible, divided by omega naught squared, which I think is about 10.6 or 10.4 radians squared per second squared. And that comes out about 0.00, 4% less. It's still going to round off to 1.2, but I'm going to say 1.15 kilogram meters squared. So there's our result for the moment of inertia.